So I'm going to explain the design task 2. So this is the circuit that I designed for design task 2. So we are going to find the weighted average and difference ratio in design task 2. So let me explain my circuit. So this is the input. I'm using a slider for both of the input. So this is the input 1. This is the input 2. This is the weighting fader 1. And this is the weighting fader 2. So let's have a look into the weighted average subsystem. So this is the weighted average subsystem. So here's the input 1. So I use the multiplier block to multiply input 1 with the weighting factor. And I use the multiplier block as well for input 2 and the weighting factor 2 as well. So after we get a result for both of them, I use the add block to add them together. So the result will be our weighted average. So let's move on to another subsystem, which is the difference ratio. So the difference ratio is the input 1, and this is the input 2. We add them together. And I use the modulus block to ensure that we always get the positive value. And after that, I use a max block to find the larger values among both of them, among two of them. So after I get after that, I will divide the modulus outcomes with the maximum number. So the result in the end we will get is going to be our difference ratio. So here is the result. Using display, here's the result as well. So I think that's all for design task 2. So let's move on to design task 3. So design task 3, we're going to build a 3-bit majority dictator. So here's a truth table. And for the question, we know that the output will go high whenever 2 or more of the input is high. So this means, in other words, the result is going to be 1 only if ABC, 2 of them are 1. So 0, 0, 0, 1, 0, 1, 1, 1. So we construct a K-map like this. So this is the equation that we get in the end. So let me explain how I get it. So first I need to group the 1 together. And the 1 must be the product of 2. Must be the product of 2. The power of 2 actually. So 2. So I only can circle 2, not 3. Yes, 4 yes, but here I can't circle 4. So I just circle 2 here. So here's my first group. So look at the first group here. I know that C will always be 1, so I keep the C. I know that B will also always be 1, so I keep the B. And the only changing is A, so I omit the A. So BC is my first term. I need to find a second group because I have 2 more 1 haven't covered. And remember, in K-map, we can overlap in. So I overlap this one. This is my second group. So for our second group, I know that AB is not going to change, so I keep AB. The things that only change is only C. So I omit the C. So that's all for group 2. So now it's a group 3. Here's going to be my group 3. I know the C is not changing in the case. I know that the only changing is a B. So I omit the B. So I remain the CA. So I cover all the 1 already. So I know that BC plus AB plus CA is going to be my final equation. So this is the equation that I designed for this. So this is the circle that I designed for this equation. BC plus AB plus CA. So BC we know that is a product, so we use the AND gate. AB we know that is a product, we use the AND gate as well. CA we know that is a product, we use the AND gate as well. After that, we use the OR gate to pass them together. So we get the result here. Basically, that is how I do it based on the equation that I found out using the K-map. So now let's move on to the last task, which is design task 4. So this is more complicated. So we're going to build a lift actually, an elevator control system. So here's some model operations. So here is the circuit that I designed. So in the design, I use the if block and the action subsystem block. So here, there's 3 input. So this input is a door open or close. So this represent the kernel flow, and this represent a request flow. So I use an if block to determine all the statement. Is it correct or is it wrong? Is it true or false? So let's look at the first statement. If U1, which is this one, is equal to 1, if it is equal to 1, this means the door is open. If the door is open, it's very dangerous. So I need to let it stop. So if the door open, it will stop. So the merge here actually is just like to merge all the subsystem block to one display. So I don't need so many display here. I only need one display. So if I only the merge will make sure you only show one outcome of the subsystem block. So move on to the second statement. If U1 equal to 1 equal to 0, this means the door is closed already. And the U2, which is kernel flow, is larger than the requested flow. That means we need to go down because the kernel flow is higher than the requested flow. We need to move down. So look at this. Yeah, move down. So the display here will show 2 because I made 2 represent 1 O. So 1 O in the motor operation is move up. So 1 O is move down. So it will move down. So look at the third statement. If U1 equal to 0, the door is closed, and U2 is smaller than U3, so U2 kernel flow is smaller than requested flow. That means we need to go out, right? So we follow the arrow, so move out. So the display will show 1 as the 1 represents 0, 1. So 0, 1 represent move out. So the fourth statement, if kernel flow equal to requested flow, then it will result 0, or it will stop. Because at the same floor, you don't need to go up, you need to go down. So the last one, the else statement, the else is like other than these 4 statements. So other than this 4 statement, the display will show 3. So let me give you for example, like the lift back down or other unexpected things happen, that it will show 3. So here you know 1 is the door is open. So the door is open, it will show it's supposed to be it must supposed to show the 0 because the lift need to be stopped. So as you can see, the display here shows 0. So it can prove that my system is going well. My system is correct. There's no error, not bug in my system. So I think that's all for me. Well, yeah, thank you.